Good afternoon, everyone. Sorry, it's late in the day. I'm sure everybody's tired and you're looking forward to the dinner. But bear with me, I'm keeping it short, hopefully. We're looking at the volumetric analysis of quick cavities using small angle neutron scattering. This work has been collaborative work. Presenting the work has been supported by the energy and collaboration of NEPSRC and also collaboration with the University of Oxford and Bristol University. Today we are just looking at some physics about small angle neutron scattering, particularly for those who are not familiar with the technique. We are looking at some of the equations and terminologies for the technique. Then I'll take you through the two different instruments which we have used for the research. One of them is the SANS 2D, which is in the UK near Oxford, and the other one is the 11 in Ireland in Brno. Then we look at the SANS data analysis, and here we are focusing on the software which is called Maxi, and in this presentation. We look at some of the metrics you can extract from the SANS data for measuring cavities. And we look at some of the examples from both copper and 316 stainless steel. Then it comes to the question whether we can really trust the data, and we will question the data. And to be able to answer this question, we looked at the repeatability of the measurements, and also we try to validate the data against two other techniques, quantitative metallography and focus ion beam cellular sectioning. I'll finish my presentation with some remarks and takeaways for today. So the physics of the small angle neutron scattering, obviously you need a source of neutron beam, which is, as I said, you need big science facilities. Examples of those I mentioned Oxford, near Oxford, and the other one is in Ireland, the one of people we are focusing today. Obviously the beam has to go through the collimation. The collimation parallel makes the beam parallel. The beam goes through the slit. The slit defines the shape of the beam, and then the beam goes and hits the sample, and the scattered beam goes obviously by it being detected by the detector. So this is a schematic view of the technique. I'm so glad the equations are coming up right. We had quite a lot of iteration through the presentation to make it right this morning, so with great help. Anyway, what you get out of the instrument is the wavelength is dependent to the angle of you get Q basically, which is the momentum transfer. What is important to take away from this slide is the importance of that what you measure is Q, and Q is inversely related to the D, which is the size of the cavities or whatever scaffold it comes from. So this is quite important, and we'll come back to this in the next few slides as well. In this slide, you will see the two different setups for the two instruments which I mentioned. I'm not going to go through the detail of this, but as a comparison, you can see that there's a D11 instrument, as you can see in the data, in the table, is covering a smaller Q range. However, the flux is larger. If you look at the table and the values in the table, comparing to SANS 2D. To be able to measure the sample using this instrument, you need to make a 1 millimeter thick of the metal you are measuring and put it in front of the beam. And depending on the size of obviously the size of the aperture you are using, because it's about 1 millimeter thick, you are measuring about 8 to 10 millimeter thick by this measurement. So this is the typical data output you get from small angle neutron scattering. Is I intensity of beam versus Q. You have seen Q before. And as I said, Q is inversely related to the size of the scatter. So I versus Q, you can see, so the larger Q gives you information about the smaller size of scatter, and the smaller Q gives you the information about the larger scatter. As it is now, you can see the information for both instruments, from both SANS 2D and D11. You can see at the higher Q, data for SANS 2D is a little bit more noisy compared to D11, but more or less the data is pretty much, they are quite consistent with each other. What is important is that we are more concerned about cavities in the Q value smaller than 0.02, and those are cavity size are greater than about 30 nanometers. So I think in terms of we are within the size range which are the two instruments are giving us consistent data. Okay, let's have a look at some of the data from the iris data. We can use the Maxwell software, which is the Maxwell software. This software has been developed in Southampton University, and more recently it has been written by C++ software program in C++ for the university. It's open source software. If you're interested to use it, I can share the software with you. So basically what it does from the iris data, you can convert the data and get the volume fraction. This is the relative fraction size distribution of the scattered VD. For the SANS, you put the sample in front of the beam and it gives you a scatter. And you don't know what is this scatter from. It's from whatever is scattering the beam, you get the diffraction. So the dotted line, it gives you the information from the reference material. This is the copper which has been diffract. The yellow dot shows information about the copper sample which has been diffract. So immediately you can see, comparing to it from the reference, you can see you will see a lot more scatter when you compare these two plots together. So as I said, to be able to from copper, pure copper, which doesn't have anything, it's pure copper, and going to a cracking material, what is the difference is cavities. So to be able to measure the volume fraction of cavities, we can basically swap the reference material from the material we have been cracked, and we can basically calculate the volume fraction of the cavity. I'm sorry, the equations are faulty, but the main equation is CD, which is you can show it you can subtract the reference, and if you divide it by the contrast factor, you can measure the volume fraction of cavities from the SANS data. So far, so good. Now there are other metrics you can measure from the SANS data. The table shows that, as I said earlier, you can measure the fraction size distribution of cavities, CD, which we have seen in the previous slide. You can measure the number density of cavities if you make some assumption about the size of the about the shape of the cavities. If you are assuming the cavities are very spherical, then you can calculate the point here, and from that you can calculate the number density of cavity, and from there you can calculate the cumulative number density of cavity. So the plot on the left-hand side, it shows you the cumulative number density of cavities for copper, which has been pressed up to 150 degrees at a different level of stress. Just take a look at the different plot. As you can see, as the stress goes up, we have got the cumulative number density of cavity increases, and that's what you would expect with the increasing of stress, when you get more cavity. So if you focus on one of the plots, for example, one of the curves, for example, let's look at the highest stress with the red dot, you can see that by increasing the stress, at a constant stress, the number of density of cavities, the number of density of cavities are increasing. Those at the smaller, for the smaller cavities, it has been the cavity inflation, but sometimes it becomes like a plateau. And that suggests that cavities are growing, and because the number of density is related to the size of the cavity, when it's the growth, the dominating factor, then you get that plateau in the growth. Okay. So, as I said in my initial slide, so we managed to get some matrix from the data. Then it comes to the question whether we can trust this data, whether we can believe the data. One of the things we looked at, we had a look at, for example, this is an example of 316 head with the version of technology we received from PDF Energy. And different locations in one sample has been examined, and you can see in the left-hand side the fractional size of distribution of the scatter for different locations. It's very similar when we're looking at different locations of the same samples. Just it's worth noting that the scale on the y-axis and y-axis in the two plots are different, so don't worry too much about it. Then I think if they are very similar, you might say, oh, they're not, but this is how much there are different. The other thing on the right-hand side, you can see the plot for a Krebs sample. This is the sample that's been a different side Krebs sample, which has been pretty great, but we are looking at the grip and the threaded ends. So those areas, those position are the position we are looking at as a reference, which I mentioned earlier. The reference points are the position we need for calculating the cavities. So the grid ends are the areas being fascinated that have seen temperature, but they haven't seen the stress. So we can reliably use those as a reference. And if you look at the four different grid samples, you can see the weight was pretty consistent in four samples. You can see there are two sets of peaks. One peak at the lower size of the 14 nanometers, and then the set of pair of the around 200 nanometers. So that's of course the repeatability. Then it comes to validating the data against other techniques. So one of the techniques we looked at is quantitative methodology. The left-hand side image, I keep referring to this screen, but I'm not trying to ignore colleagues in this end. So anyway, the back image shows from figure 6, cavities are usually separated between boundaries around the fibers, which are brighter in the back image. And at some point, more systematic cavities intergranular, which you know that see. So this sort of images we can take, and we can quantify them by adjusting the contact factor contour. You can separate these cavities from fibers and quantify the cavities. There was an interesting talk this morning about using the AI for quantitative methodology. I didn't have a chance to talk to the talk, but I think that obviously what I present here is quantitative methodology data on the 2030 image. But if you would imagine this could be open minded and AI could help this to improve enormously. So moving on, from the same samples, you got the sample data on the right hand side. So different plots show different level of strain. So as you can see, by the freezing constraint, the amount of cavity behind the polyfraction of cavity increases. And again, you can see the two sets of smaller and larger cavities in this material. This shows the quantitative data, quantitative data and SANS together, measuring this is the mean versus the strain to the failure. And as you can see, the difference between the two techniques is pretty consistent. You can see smaller cavities around 25-40 nanometers, and larger cavities about both techniques around 100 nanometers. So there are good agreement for this material. So I hope you agree with that. So the other technique we use is deep cellular sectioning. For this, from the copper data I showed earlier, the number density of cumulative number density of cavities measured by SANS in this in the copper. It's about 2.5 power of minus 40, which is more or less about 1 cavity per 40 millimeter cube. So we wanted to have a look at the deep serial sectioning and see what we get for this material. So I hope this video will play. So it's only about 30 seconds. So you can see whether you slice with the material, you can see the cavities coming through and disappear through the section. So I'll let it run. By this, in this specific sample, we spotted about 47 cavities in the area which we sectioned, which is about 1 cavity per 200, and that should be 200 micrometer cube, not millimeter cube. So I think it was sorry for that. The area you're covering with the deep serial section is the micro volume comparing obviously to the SANS. It's a very challenging technique, obviously, because the cavities are inhomogeneously distributed in the sample, and it's very you must be lucky to hit the correct area and to be able to quantify substantial number of cavities to be able to translate and calculate the quantitative measure of cavities. So it is challenging, but it's doable. So in summary, SANS is a powerful technique for volumetric measure of cavities. As I said, you're measuring about 8 to 10 millimeter cube. There are some useful information you can extract from the data, but you need to make some assumption and you need to know the sample, for example, by metrologography or other technique. You need to know what is the shape of cavities and what are the distribution and what is the nature of the cavities and carbots. For example, if you are looking at the 316, for example. We look at the two sets of data for the SANS in two different SANS instruments, and they were pretty consistent. Also, we compared the SANS cavity measurement from compared with quantitative methodology and also deep serial sectioning, and as you saw, there were agreement between the data sets. So, as a final remark, I think we could confidently use SANS for research investigation in high condition material, not for the current material, but for the future material as well. So these are some of the people who help for the work to happen. So it's just acknowledgement. So